continue our fascinating discussions with public lecture series. Using this spring school, Professor Angelo Bassi has kindly agreed to give a public talk entitled "Believe in a Quantum World." So please, thank you very much, and please.
Thank you. So this is, so for those of you that follow the previous lectures, it's again about very world, which is, at least in my heart, as the core issue in understanding what it means to live in a quantum world. But it's done in a different way, so it's for a general public to appreciate. That also means it's useful for people more experts like you to appreciate what are the issues at stake here. So what is the first striking difference between classical mechanics and quantum mechanics? Classical mechanics is described, I'm thinking about massive particles, so not taking into account the electric field, the electromagnetic field, the gravitational field. It's described in terms of particles. Particles that have a position in space and move along trajectory. The point, so we have in mind always point-like particles, that's not so important, whether they are point-like, it was also TBAE, it's really point-like in the sense of a point of zero size, or is it a little ball? This is a conceptual issue, experimental challenge, it's not important, it's particle in a loose sense, but they have a definite position. And actually, this is the first property that the objects have, no? If you have to think, what is the first property of an object? To be classical. It is somewhere. Then it is round, I'm tall, and I'm not tall, and I'm young, and old, blue or white, whatever, but the obvious thing that no one thinks about, except for mothers, when they have to think about their children, where they are. They must be somewhere. No? So the objects are somewhere. Quantum mechanically, you have waves. And it would be interesting to see, so it would be actually could be another lecture, why, in the very first place, I don't know if you remember, if you had a quantum mechanics course, how the concept of a wave entered into quantum physics. The concept of the wave entered, no thanks to de Broglie, if you remember, or if you have learned about that. So why de Broglie introduced waves? So in quantum mechanics, object matter is described as waves. Now you buy it, then I come back to de Broglie. Yeah, you buy it. So if you learn quantum mechanics, you learn that and you accept that. But in a certain sense, why waves? Instead of in measurements, you don't see the waves. You see the particles. The detectors click. So why the wave was introduced in the very first place? The wave. It was introduced by de Broglie to explain discreteness of the atom. No? The point at the time was that the classical model of the hydrogen atom was inconsistent because the electron should radiate, the electron. So it was an experimental important discovery to know that there are protons, electrons. Electrons are more or less point-like, and so they go around the nucleus. But then if they go around, that's an accelerated motion. They should emit radiation. They shouldn't fall into the nucleus. And then Bohr came with the Bohr model that tried to give a partial explanation. Bohr also tried to explain the spectral line. And the bottom line of the Bohr models is that there are discrete energy levels. And that's where de Broglie basically enters. De Broglie, with the wave, the hypothesis, was capable of explaining discreteness. The continuous idea, the wave, you explain discreteness, why there are discrete energy levels, which are the levels where the wave closes. So a classical concept to explain quantum properties. But there is a fundamental difference between a classical wave and a quantum wave, which is never always fully appreciated. The fundamental difference is that, so what is water waves? There are waves. But it's waves, these waves are made of molecules that are always somewhere. The wave can split in two. But each water molecule, the water molecules do not split in two. Half water molecules, so to say, compose one part of the wave. The other half of the water molecules compose the other part of the wave. So waves superimpose, they do whatever they want. But they are a collective behavior, while matter is always localized in space. It's a classical matter, always somewhere. Quantum mechanically, that's the big difference, is that the wave is associated to a single element of matter, to a single atom, to a single electron, if you wish. And so that is the question. What does it mean that matter, so that an electron is described by wave? So I come back, basically, will be a review of these 3 days of lecture. What does it mean that the electron is described by the wave function? Now, of course, the textbook thing says it means that if you have a superposition, you cannot predict the outcome of the measurement, and will be, depending on the wave function, will be 50% of one part, 50% of the other side, whatever. But yes, that's okay from the making experiments. But physics is also understanding before experiments. You want to understand things. What does it mean that an electron is described by a wave that is in superposition? Again, as I said in the previous hours, there is no answer in the sense that you can have more than one answer, and the moment they are both satisfactory. So waves superimposed, and that's the question. An atom here in the picture. If you really think an atom, so we are made of atoms. We are solid. We are very solid. What does it mean that an atom can be in superposition? Is it 2 atoms? No, we know it's not 2 atoms. 1 atom. It's half atom? No, we know it's not half atom because it's all. The atom cannot divide into half atoms. You can break the atom, and you cannot divide it, cut it into half atoms. So it's really, it's one of the fundamental questions in quantum mechanics that you can forget about. You can do the rest of physics in a peaceful way, but perhaps you might want to insist also on this. The question becomes more interesting when you have the superposition of many atoms, and theoretically. So now experimentalists are slowly pushing the limits of quantum mechanics. So now we know how to make a superposition of 2 atoms, 3 atoms. The current record is the superposition of 10,000 atoms, which is amazing from the experimental point of view, but still it's nothing from the point of view of foundation. So these are wonderful experiments, but they don't answer the question. Now we come to Schrödinger, and the cat. What does it mean that the cat is in a superposition of being dead or alive? I did not spend too much time, you know about the Schrödinger cat. And also, perhaps the thing that you know less is that the environment, the coherence, doesn't play any specific role in answering the question, because I'm using quantum mechanics. The cat goes in the superposition, and also the environment goes in the superposition. If you take environment into account, it's even a larger superposition. If you make it even more dramatic, what does it mean that the universe is quantum? If you take a quantum cosmology perspective, that quantum theory is the fundamental theory. Quantum theory, I'm talking about the quantum framework, so quantum field theory, quantum string theory, loop quantum gravity, whatever it will be. It's a quantum theory. Quantum means a unitary evolution, means a superposition of some sort. So if we live in a quantum world, and the world is quantum, and quantum cosmologists teach us that the initial state was the vacuum state, the Bunch-Davis vacuum. I'm not an expert in cosmology, probably some of you here already knows more than me. which is a completely isotropic state, and you let it evolve with this evolution, the final wave function, the final state of the universe, is nothing to do with what we see today. The full state of the universe. It's completely isotropic, and certainly the world is not isotropic, otherwise we couldn't distinguish it. So how can we make sense of the world that we live in out of quantum mechanics? These are the open questions that brought Einstein, brought Schrödinger with the cat paradox, and then brought the people working in the field of quantum foundations to not to question quantum theory, but try to make sense of quantum theory. There is truth in quantum theory, a lot of truth in quantum theory, but we have to understand, still to understand what that truth is about the world view that emerges. Because the first, so physics is important for many reasons. It's important for technology. All this, basically most of these lectures at some point have been towards technology, but the first goal of physics is to create a world view, to understand the world that we live in. What does it mean? So if you really think, what does it mean that the atom is in a superposition? This is not an easy answer. And again, as I said in the previous slide, I will not answer the question because there are several answers. That's part of the debate, and we wouldn't go anywhere. We still, the fact that there are several answers means that we are not understanding what the answer to the question. And so I come back to Einstein and Bohr. I come back. The two, so it's what I said before. The two big possibilities that you have to choose among them, and we don't know which one is the correct one, is completeness and incompleteness. Incompleteness means that the wave I told you, the wave is not the full description. It's the way it works. And actually, that was the original, or it seems to be, the original idea of de Broglie. De Broglie didn't want, in a sense, to replace particles with waves. De Broglie was more inclined, at least in the first part, or in some part of his scientific evolution, he was more inclined to let particles, as they are, point-like particles, but to associate a wave to the particle. So that's why people talk about the de Broglie theory, the pilot wave of the Broglie theory, as I told you before. Instead, so just to make the analogy, a classical particle is like a person walking on the street. You go straight. A quantum particle is a surfer on the wave. You can't go straight. You can, if you're really not, perhaps, but you have to cope with the wave, and then you, whatever happens, happens. So that was the original idea of the problem. So there is a way, now we know, experimentally, we have seen it several times, we cannot ignore quantum waves. But the wave is not everything, if you take this point of view. There is something more than the particles. So why do people insist on particles? Because we see in objects. It's me. You can cut me in 2, 3, 4 feet. There is matter. So you want to explain this obvious fact of empirical evidence that you don't even think about. There is a solid matter. Waves are not solid. Or the completeness assumption. The wave is everything. But then I'm not the wave, what am I not the wave? So you see, there are problems in both things. There are due to the wave. Bohr, so Einstein and Bohr, of course, I'm simplifying a debate and an evolution that is much more complex and rich and richer than what I'm going to say. That's the job of who studies the histories of physics and the history of quantum mechanics in particular. I'm just making a simplified assumption with all the limitations of that. So Bohr was taking into account, was a champion of the orthodox way of understanding the quantum world, and he was specific about that. So you have to buy. So if you accept completeness, or completeness, what is it? Bohr. If you accept completeness, you accept in the way that Bohr understands it, or Bohr not in the sense of a person, but in the sense of an entire environment, because I'm Greek, not an expert in specifically Bohr's point of view. The wave function describes the outcomes of measurement. So the wave function is not real in the sense that we are waves that fly. Also because the wave function is not in real space, it's in the input space. The wave function is a tool to describe experiments. And then if you ask the question, okay, fine, but what happens in between experiments? So when I fly a particle from the source to the detector, what happens to the particle? The answer is you cannot ask the question, because you can only speak about outcomes of measurement. So you are imposing a significant limitation to the power of physics. Physics is only about outcomes of measurement. It's a point of view. Einstein was certainly against that. Measurements, here, no one experiments, are fundamental for understanding physics, but physics is something more than describing experiments. It's about providing a worldview of what we are from physical perspective. Of course, there is philosophy, religion, if you wish. We are just talking about physics here. What worldview physics provides, then experiments will tell whether this is right or wrong. But experiments are not everything. They are important. They are important. Crucial important. Okay, so I quickly go again with the particle in the box. So Einstein said, I don't care about outcomes of measurements. Not because I'm doing theoretical physics, I'm not an experimentalist. I'm okay with the outcome of measurements. But I want to understand what happens in between measurements. When the particle flies from the source to the detector, is the particle somewhere? The wave diffuses. The mathematical wave, the wave function diffuses. But what happens to the particle? Is the particle a particle that is always somewhere, but I don't know where? Or does the particle disappear? Personally, I think it's an important question to assess, theoretically, conceptually, not experimentally at this stage, because you're not talking about experiments, you're talking about what happens in between experiments. What image of the world am I willing to accept that emerges from quantum theory? Is this particle always somewhere? And most physicists, in an indirect way, would say so, because then I want to challenge particle physicists at CERN, telling me that particles disappear in between measurements. They're not there anymore. They vanish. They don't exist in between measurements. Then, if particles exist always, then where are they? Can I say that they are somewhere? They are anywhere? They are in a point? They diffuse? That's what Einstein was bothered about, and other people, of course, with quantum theory. The wave function doesn't answer the question. So the wave function is an incomplete description. Bohr, Isaac said, no, useless stuff. So just not important. You can choose which camp you feel more comfortable. So Einstein said, no, I insist that I think that the theory is incomplete, that there is more than the wave function. The wave function does not provide a complete description. I'm not capable of convincing you by arguments. Look, you should have to go beyond the wave function. I'm not capable of shaking you this way. Then I will shake you another way by proving that if you do not buy incomplete, if you don't accept incompleteness, then your theory is non-local. Like I said, it's a talk about non-local. It's a particle in the box. So you have the particle in the box. Now, I have a nicer picture. I have the shaded region represents the wave function. The wave function is uniform in the box because you don't know quantum mechanically where you will find the particle. If you make a measurement, it will pop up anywhere. So you have a uniform probability, you split in two, you separate the two parts, and you ask the question, where is the particle? Now, the incompleteness assumption is that the question is meaningful. You can ask the question where the particle is, and the answer is very trivial. The particle is somewhere. You just do not know where. It happens to be on the right side. So the wave function doesn't tell you where it is. It's not a big deal. It's somewhere. The wave function doesn't. It's incomplete. It's good. It's a wonderful tool, but it's not everything. And only when you make a measurement, and you look inside your part of the box, you don't see the particle, no big deal. It was there all the time. Nothing special happened. It's classical situation. Of course, Einstein was not so naive to say that quantum mechanics is a modification of classical physics. Certainly not. But the structure of quantum mechanics is that of a statistical theory, like classical statistical mechanics. So the structure is similar. Then the theory will be much more complicated, and Einstein was aware of that. But then if you apply the completeness assumption, then something different, completely different emerges. So if you say, look, if in this situation, the wave function doesn't tell you where the particle is, because there is no fact whatsoever about the position of the particle. You have to wash your brain completely, your mindset, stop thinking about particles. The word particle is misleading. There is no particle in the sense of being located somewhere. There is no fact in nature about the position of the particle. And why there is no fact about the position of the particle? Because the wave function doesn't contain that information. Of course, the particle must be, it cannot be here. The wave function is zero, so there are always some facts. The wave function is zero, so the particle will certainly not be here. The particle will be either here or there. So there are some facts about nature, but not the fact about the particle being here or there. And if you think so, if you see if a particle is just something, but if you think that the particle is part of your body, and then you think that there is no fact about that part of your body being anywhere, you have to buy it. If you really stick to that and fully understand the implications of that. And when you make a measurement and you find and you see that the particle, you look all over the place here and the particle is not here, then you know that, well, you don't, now the picture is a bit misleading because you don't know exactly where it is, but you know that the particle must be there. So what happens here? That before the measurement there was no fact whatsoever, no, if you want to use a philosophical word, there was no ontology about it. Clear. Now you have an ontological statement, the particle is here. So you change things. By doing a measurement here, you change things also on the other side. One should appreciate, so the people at the time didn't appreciate it. That's the important, the first insight of Einstein, and he was the first one, and probably the first one, not the only one. Heisenberg, in a paper, agreed with Einstein. Heisenberg said, and there is if you look at the history, Heisenberg, champion of orthodox theory, says, yes, you're right, it's a non-local phenomenon, but who cares, because you can signal. So at least in words, the no signaling theorem is due to Heisenberg in the 20s, at least in words. So Heisenberg acknowledges in one, this is what they read, the quotes that they read. So it's a non-local effect. Then if you say who cares about this non-locality because it has nothing to worry with relativity, that's another story. Einstein didn't care about this. He didn't care about it's a non-local effect. I don't buy non-local effects, and for that, so there is. So the issue is not so much being compatible with relativity or not. Einstein, when Einstein made theories, he was always willing to modify them. When Einstein developed general relativity, the day after he was unhappy with general relativity because it's an unbalanced theory. When you have the Einstein equation on the one side, you have the beautiful part of the metric, the geometric description of gravity, and on the other side you have the messy, the stress energy tensor, a very messy description of matter. Einstein didn't like it. He tried to change, to geometrize it. Also the other forces, he didn't succeed, you know. But Einstein was very willing. That's why also he played the cosmological constant. He was very willing to modify theory. There were attempts. And probably, I don't know that, that's my guess, it would not have been sacrificed his life for special relativity. But for one thing, locality. For him, locality comes before. Locality for him, the locality of interactions comes before because locality, it's because of locality that eventually, if you really think about that, and Einstein was wrong, I think, on this, but it's a different thing, you can think of isolated systems. So locality for him was the prerequisite for doing physics. Physics, if you cannot identify systems, you cannot build the physical theory. So locality for him was the first ingredient in order even to think of how to build, make sense of a theory of nature. Then, on this was all. You can do very reasonable theories also that are non-local. I'm talking conceptually, then, with experiments, a different story. I'm talking about a matter of principle. Okay, so the quest of locality poses a potential problem with quantum theory. And now we come to Bell. So now it's the story of Bell in a popular way, but I think it's interesting for those that are not exposed to quantum theory to understand what happens. But also for those that have been exposed to quantum theory to really appreciate the contribution of Bell, which I tried to convey previously, and let's see. This is another way of looking at that, and hopefully it will add something for those of you that already followed my other lecture. So this is a story again, it's always Alice and Bob. But now there are just two characters of television. They say that they go around the world with a show. They make the following show that probably is more appreciated by people my age and older that saw these TV shows with the, where you had some like telephone booths where people entered in order to be isolated from the outside. Now, I don't know if they use that anymore. They had also headphones in order not to hear whispers around to guarantee that they are fully isolated. And then there was a quiz, you ask questions, and they had to answer if they answer correctly. They won money. Now, with the new technology, you cannot prevent anyone having a small piece of a earphone in your ear. Someone can suggest the answer to the question. Okay, so it's a kind of an old-fashioned game. So Alice and Bob, they are two mates. They go around and they make the following game. So they go on two opposite sides of the planet. So one here is here in Istanbul. What's opposite to Istanbul? I don't know. In Italy there is New Zealand. In Turkey, it's water on the opposite side. I don't know. On a boat on the opposite side. And they say the following thing. So they are isolated, so one can check with all the possible technology in this world that they are completely isolated. They cannot communicate in any way whatsoever, according to the laws of physics, of course, with one with each other. And the game is the following. There is a public, one here, one there, and the public, so it's a silly game because we are reproducing Bell inequalities, but when you make it macroscopic, I think it's more impressive. So there are two publics, and the public, they give the card. So there is a public here in Istanbul playing with Alice on the boat, or wherever it is, on the opposite side of the earth. And there is Bob, isolated. There are some public also on the boat, and they give cards to Alice and Bob. A card either with the number 1, or with the number 2, or with the number 3. And the game is repeated because it's quantum, so you want to build the statistics. So the game is a silly game that is repeated with the round number 1, round number 2, 3, 4. The public decides, so they go repeatedly, the card, with some frequency, whatever it is not important. The public decides the number of the card. The public can agree or can go independently. Suppose that the two go independently. So here, the public chooses a card with the number, whatever it is, and goes on the other side. They don't talk to each other, they don't care. We want to make it fascinating, to make it non-local. The public, within, I mean, the experimental possibilities, they do the two rounds go on simultaneously, so that the public cannot agree on the card to give. They cannot even agree because they give simultaneously within, again, experimental limits. If you don't like that, because it's not easy, one goes on Jupiter. The cards. And almost simultaneously, Alice and Bob react, so that it's no physical signal can connect the two, to make sure they cannot connect it. So that's the game. Alice receives a card with the number 1, number 2, number 3, and then she does a simple thing. She writes on the card yes or no, and she gives the card back to the public. It's a very stupid game. It is. But that's the game. So, card with some numbers, and the card comes back with the yes or no. And the same does Bob of the other stuff. So far, no one would be interested in that. But then comes the claim. So this is an example of a round. Outcome of the game. So 8 rounds, I picked, there are many more. This is the choice that the public, for the card that the public made. For Alice, and the one for Bob, that now we know afterwards. And that are the answers given by Alice and Bob. So apparently, nothing, no big deal, just a silly, a dull sequence of events, except for one thing, and that's what makes Alice and Bob famous in our story. That they say, look, do whatever, they tell to the public is us, do whatever you want, but be sure that every time that we receive a card with the same number, we give the same answer. And based on this, we claim that we are telepathic. So if you really try to picture in your mind the situation, these two guys separated, the two things go on completely independent one of the other, completely independent one of the other, but unavoidably, if they receive the same card, they give the same answer. Both yes or both no. They are telepathic. That's what they claim. Telepathy is not locality in the sense of they can think, they can instantly read in the mind of each other. What are you doing? Yes, I do the same. It's exaggerated. It's just an analogy to very important. So that is the game. Let's see. Okay, so now you know it, so you give me the answer. But then when I ask to, when I tell this to a general public that doesn't know about Bernoulli qualities, it's interesting. The reaction is always interesting. So do we buy this? The question is always the same. Do we accept this? Alice and Bob really are so amazing, these two people that can react in the same way, even if they are far apart from each other. Do we give credit to these people that say so? Anyone who wants to say anything? So if that happened, not here on the stage where I'm talking, but if you read that in the news, you wouldn't believe it. Really think that now that it comes on the news and now all the media start to report it, even larger and bigger titles on the newspapers, amazing, telepathy has been proven. You wouldn't believe it. And in fact, there is a simple explanation that will be spotted immediately. There is a simple explanation to their supposed telepathy. Very simple. They agreed the answer before starting the game. You know, now that reminds me of the lecture of Vanini yesterday about cryptography with the Enigma thing that the guys had a booklet with the keys. Here is the same story. Alice and Bob, it's not the same story, it's the same tool but for a different reason. They had a booklet where they pre-arranged the answer. And with modern technology it's even easy because you don't have to have a big booklet, it's just for the mobile phone. The mobile phone is isolated, you can't communicate, that's the game, you cannot communicate, but who cares? Because you initially stored the information on the phone. So the phone is isolated like Alice and Bob, they don't talk to each other. Mobile phones don't work in this game, in this world, for communication, but for storage of information, yes. So they had a booklet and they agreed before starting the game on the answers. And they agreed, look, in the first round, if we receive the card with a yes, with number 1, we answer yes. If we receive a card with number 2, we answer yes. But if we receive a card with the number 3, we answer no. In the second round, they make things up to confuse people. We just do something different. If in the second round we receive a card with the number 1, we answer no. If we receive a card with the number 2, we answer yes, and then no. And then you can go on with the So that is the point. This is the EPR. No? I hope you should have recognized that. But this is the point of Einstein. Are you willing to buy telepathy, yes or no? If you buy telepathy, if you buy non-locality, quando non-locality at the end you have to accept it. If you buy quando non-locality, end of the game. But if you don't buy non-locality, if you insist, it cannot be, come on, things cannot be correlated instantly. Then you look for an explanation. I think this is typical. So when you have correlations, they call for an explanation. Why are they correlated? No, that happens in statistics. No, when you see correlations, you want to understand why they are correlated. It's a very simple thing. Einstein was doing these things. Why are they correlated? And the answer is, well, they agreed beforehand. And that's, you see that by reading the booklet, so I come back to the previous situation, the public decided in the first round to give Alice the card with the number 1 and Bob the card with the number 3. They read on the booklet, 1 means yes, 3 means no, yes and no. And then it's obvious that if they both receive the card with the same number, 2, they always will give the same answer. That's no big deal. It's very trivial. However, let me go back. That there is a deep implication. What does it mean that they agreed, they had the booklet? They had some extra information that they didn't disclose to us. They didn't say the full story. They told us part of the game, but they didn't tell us the trick. So there is extra information that was not available to us. Incompleteness. We didn't have the complete knowledge of the game. Or, in physical terms, the complete description of the system. This is incompleteness. We know part of the story, we do not know the whole story. So that is the game, the major message of this first part of the game, which is Einstein. Locality, so I cannot be. This instantaneous correlation of Alice and Bob needed a call for an explanation, because I believe that they must have a common source. They cannot jump out of nothing fully correlated at a distance. Calls for an explanation, so extra information, hidden variables, incompleteness. There is something more than the wave function. Quantum mechanics is beautiful, but it's not the entire story. There is something else in the description. So it is, again, if you are interested in the foundations of quantum mechanics, so this is an important thing to assess completeness versus completeness. Practically, the world will survive to this question. But it's for understanding the worldview, or if you want to put it in economical terms, monetary terms, are Alice and Bob rightfully becoming famous and becoming rich with this game, or poor cheapers? But now Bell comes, and that's I think in this way the intuition and the contribution of Bell is even more important. Bell, at the end of the day, did not went behind Einstein in the sense that he was not interested only in these beautiful correlations when Alice and Bob received the car with the same number. Of course, you know, car with the same number means spin measurements are in the same direction. It's just a popular, another way of saying the same thing. He says the following thing: let's look at the entire statistics. Let's look. So suppose that they have this book. So they predefined the possible answers. Fine. They are cheaters. But let's look at the book. Now, what is the statistics? The statistics is the following, that if they receive, in the first round, just the first round, then you repeat the game for all the other possible choices. So in the first round, they agreed to answer yes, yes, no. What does it mean? It means that if they receive the card with the number 1, of course they agree. A means agreement. So if they both receive the card with the same number, that is the diagonal, if they receive a card with the same number, they give the same answer, so they have an agreement. But what happens if they receive a card with a different number? If Alice receives a card with the number 1 and Bob receives a card with the number 2, 1, 2, they will still give the same answer. Only if, for example, Alice receives the card with the number 3 and Bob receives the card with the number 2, 3, 2, different answer. Agreement, disagreement. And then you can do the statistic for all possibilities. So this was a yes, yes, no. But it could have been no, yes, no. You can do all the possible cases, and you will end up with the following thing, that if they had this booklet with all the possible answers, then statistically speaking, the number, looking at the entire sequence, not just when focusing on when they receive the card with the same number, but also when they receive a card with different numbers, the number of agreements should be greater than the number of disagreements. That is another version of Bell's inequality. Locality, Einstein, locality means there are 3 arrangements. Now Bell says, okay, there are 3 arrangements, then I have this inequality. They should agree overall more times than when they disagree. Okay, fine, let's go back to the same story. This is the same thing I told you before. 8 rounds, the yellow things are where they receive the card the same number. The blue things seems nothing special, but let's count the number of agreements and disagreements. Substantially equal, within statistical error. That is the amazing result, experimental result. So this is the test of Bell inequalities. The inequality is boundary. So that is, what does it mean? The journey started with locality assumption. Einstein will say, no, cannot be, no telepathy. And we end up with the inequalities. The inequalities, now the experiments come, the inequalities are violated, and so we have no locality. So these correlations that pop up here and there when you have entanglement, so these Alice and Bob giving the same answer, perhaps they have a common origin. We don't know. They pop out of nothing, they have a common origin, whatever there is, but statistically they give a sign of something non-local. You cannot explain them in a completely local way because of this common source moves subluminally and goes here and there. Such an explanation is not compatible with experimental. So, nature is non-local, so quantum locality poses, I think, a serious problems with respect to relativity, which is based on the principle of locality. The conflict is not direct. It's not that physics is falling apart. I mean, Bell is from 1964, and we are still here talking about quantum field theory and quantum gravity, so it's not that physics fell apart. But there is an indirect, the conflict is not direct because of the no signaling theory, of course, because of that. But it's there. It's still, this tension is always there, and still no one knows what to do. We are at the frontiers of our understanding the quantum world, and we haven't understood yet. There is no big deal. I mean, we cannot seriously think that we understood everything. There are many things that we still do not understand. Of course, this is for the general public. Now here you will know that these arguments, remember that Wolfgang Pauli dismissed the complaints of Einstein, saying that the question, more or less the question that Einstein raises, are equivalent to asking how many angels sit on the top of a needle. Useless question. How many angels can sit on top of a needle? Who cares? How many? It's not our business. That was the attitude at the time. It couldn't be more wrong. Einstein, EPR, Bell inequalities, entanglement, you know now after these lectures. It's quantum technologies. Cryptography, in particular, quantum information processes. So I give you the perspective that already. So these are important questions per se, and the recent development of the history of quantum mechanics, proved that they were important also to the point of technological development. So I stress one point which is important, that these different, so correlations are also classical. This non-locality was also part of classical mechanics until the advent of special relativity. The big difference of this quantum non-locality is that it's insensitive of distance. It doesn't decay with the distance. It becomes more difficult experimentally if the distance increases. And so this is a personal assessment you might easily disagree with, in the sense that you have, I think that calls for a new theory of space and time, of course, where distances are not, absolute distances are not there anymore. Because no locality. No locality has that you can have effects that are not sensitive to distance, but which can have a nice opening to a nice worldview. So if you really think of the universe as a quantum thing, which is a huge entangled state, which is a vastly correlated state, we are not independent. We are all connected. If you take, you really, I'm suggesting you to take quantum mechanics even more seriously than it is usually taken. Not to dismiss quantum mechanics, to take it even more seriously. The wave function of the universe is a huge, crazy state. We emerge. We must emerge from the, it's not that, in the sense of a description, not that we emerge from the wave function, not in the sense that physical sense that there is a wave function we emerge. That our description as physical systems should emerge somehow from the description of the wave function. This wave function is entangled. This entanglement is non-locality, a correlation that go behind distances. We are part of that. If we take quantum physics seriously, which means that we're all connected, which is not a bad perspective. Instead of isolated islands that ignore or fight against each other, we should think of ourselves as connected people, that we should cope with each other. Okay. So what about the cat? The story started with the cat. As I said, the question is still open. You can take the orthodox point of view, you can take a different point of view, but the cat, I mean, is safe, the cat, because you can easily explain the cat is not in a strange state, the cat is dead or alive, we live a, if possible, happy classical life as macroscopic systems, although emerging from a quantum world. Okay, thank you for your attention.